Hello, welcome to my Sigmetrics tutorial on predicting time to event outcomes. This tutorial gives a tour of survival analysis from classical to modern. I'm George Chen and I'm a junior faculty member at Carnegie Mellon University. I previously taught a version of this tutorial with Jeremy Weiss at last year's conference on health, inference, and learning. And the older version of this tutorial had much more of a healthcare focus. So survival analysis is about predicting time to event outcomes. Examples of these outcomes include time until death, time until a disease relapses, time until hospital discharge. Another way to put this would be hospital length of stay. Time to event outcomes don't have to be about healthcare. To give two examples of time to event outcomes that are not healthcare related, one would be predicting time until a convicted criminal reoffends. This is called recidivism. There's also predicting time until a user unsubscribes from a service, such as a movie or TV show streaming service or a music streaming service. There are, of course, many more examples of time to event outcomes. In this tutorial, to keep the terminology easier to understand, I'm mostly going to phrase terminology in terms of this first example of predicting time until death. This is also the example that researchers initially focused on when they studied survival analysis, which is why the field is called survival analysis. So the outline of this tutorial is as follows. I'll first go over the basic survival analysis problem setup. Then I'll talk about some classical estimators and how we assess prediction error. Then I'll go into recent neural net advances from the machine learning community. Finally, I will talk about open challenges. At the end of this tutorial, I will point out some software packages. And lastly, before getting started, I'll mention that all the material you're seeing here are posted on this web page that's shown on the slide. All right, so let's get started with the basic survival analysis problem setup. In survival analysis, our data looks something like this. We have a bunch of patients, or data points, and we have a bunch of features, okay? So this example that I'm showing you is a healthcare example. And for simplicity, here, let's say I have measurements that are either a check mark for +1, an X for -1, and if it's missing, I put a 0. Of course, you can have measurements that are not just binary or 0 for missing. You can have continuous valued features. And the label that we're trying to predict is the time until death, okay? So basically we have our feature vectors, and then we have these durations that we're trying to predict. And note that in our training data, as is common in survival analysis, we typically cannot wait for everyone in the training data to die. So that's why for this last patient here, there's this greater than or equal to sign right here. This means that when we stopped collecting training data, this green patient was still alive, and that's why their time until death is at least 6 days. Okay? With that said, you can think of survival analysis as essentially like a special kind of regression for predicting time durations. These durations are always non-negative, and then we have this peculiar feature where we can have this greater than or equal to sign. Just to anchor some notation, for the ith person, I will use xi to denote the ith person's feature vector. The next thing is I will use yi to denote the observed duration. I'll also refer to this as the observed time. So yi for this green patient is equal to 6, okay? And then we also keep track of what's called the event indicator delta I, which is in this example saying does the person die or not in the training data. Because we have this greater than or equal to sign, this patient was still alive when we stopped collecting training data, so delta I would be set to be equal to 0, meaning that death did not happen. Whereas for the first patient that we saw, person 1, the feature vector would be denoted as x1, and the observed duration y1 is, in this case, is equal to 2, and whether the person dies, the event indicator delta 1 is equal to 1 in this case. Okay, we don't have the greater than or equal to sign. We actually do observe the time until death. So with that being said, we have our training data, which consists of the feature vectors, the xi's, the observed durations or observed times, the yi's, and the event indicators, the delta i's. And what we want is for a new patient or a new data point with feature vector x, okay, so a test feature vector x, we want to be able to predict the probability of surviving beyond time t condition on the feature vector x. Okay, so this I'll refer to throughout this tutorial as s of t given x, also called the survival function or survival curve. Note that this is a function of time, and so a survival curve looks something like this. Okay? Note that unlike in the standard regression setup, we're not just predicting a single time, we're predicting this whole curve. And this curve, note that it monotonically decreases. It starts at 1 and then it decays to 0. Okay? The other thing I'll say is that we have different survival curves for each feature vector x. And also, if you did want a point estimate for the survival time, there are different ways to back it out once you know S. I'll give you 2 example ways of doing this. One way is you look at where this curve, this blue curve, crosses 1/2. Okay? Where it crosses 1/2, you look at the time. This is referred to as a median survival time estimate for feature vector x. Okay? As another example of how you can back out a point estimate for the survival time, is you can look at the area under this blue curve, okay? And this gives an estimate of the mean survival time for feature vector x. So I'll say a little bit about interpreting these survival curves. What the time to event outcome is matters here, okay? So for example, if the outcome is time until death, then typically longer is considered better. Okay? Whereas if you were looking at an outcome such as hospital length of stay, usually longer is considered worse. So depending on your time to event outcome, you need to have some idea of directionality, whether longer time until your event is considered better or if it's considered worse. So with that being said, we have this blue curve here. For a different feature vector, perhaps the survival curve looks like this purple curve here. Okay, and so if the outcome is time until death, then we would typically say that the purple curve is uniformly worse than blue because the probability of surviving beyond any time t is less than the corresponding value for the blue curve. Okay? Of course, it's not always the case that you have one data point survival curve being uniformly better or uniformly worse than another. You can also have this behavior where for a different feature vector, the survival curve can be this green curve where it's not always better than or worse than the blue or purple curves. Okay, so sometimes it's better, sometimes it's worse. And of course, you can also, instead of comparing the different curves, you can compare the mean survival times, so the areas under the 3 different curves here, or you can compare the median survival times. So you look at the times at which each of these curves crosses 1/2, and you compare them to see which curve has smaller median survival time versus larger median survival time. Okay? All right, so the next thing I'll say a little bit about is theory. In this tutorial, I'm not going to go into any sort of details on theoretical guarantees, but it's good to know a little bit about when we should even expect the estimators to work well. So one thing that is the case is that we cannot estimate the survival curve arbitrarily accurately for all of time. Okay? One intuitive way to think about this is that even in the training data, there's some maximum observed duration that we see. So for values of t larger than that maximum observed duration, our estimate for the survival curve will just be some sort of extrapolation, okay? So typically in theoretical analyses, people will focus on estimating S of t given x accurately just up to some time horizon. So another thing I'll say is that the censoring mechanism and also the censoring rate do matter a lot in practice. So just to give an example, basically survival estimators will tend to work poorly if you have high censoring rates. What do I mean by this? For example, if you're predicting time until a hard drive fails or time until a musician gets signed by a record label, both of these prediction tasks are very hard, and part of the difficulty is that very, very few hard drives fail, right? So the percentage of data points you have that are not censored for which you actually do see the time until failure is going to be very, very, very tiny. Similarly, among artists trying to get signed by record labels, the fraction of them that actually do get signed is extremely small. And so if you're trying to predict time until a musician gets signed, most musicians, they're going to be censored. At any point, if you stop collecting data, most musicians didn't get signed yet. Okay? So if you're in those regimes where you have high censoring rates, you're going to run into trouble. And if you do want to do prediction in those settings, I would recommend first solving a simpler classification task to basically narrow down the cohort of people or hard drives that you're looking at to the ones that have a higher fraction of failure. And then among those, you do some sort of time to event prediction. Okay? Because like I said, otherwise survival estimators, these typically don't work well if you have high censoring rates. By the way, what I put on the slide here is, it's kind of a made up number. What's considered a high censoring rate kind of varies by application and method and so forth. In a lot of papers, 40% or higher would be considered like a fairly high censoring rate already. Something else I'll briefly say is what the typical theoretical setup is. So just like with standard regression and classification theoretical analyses, we assume that the data are generated IID. But now it's a little bit more complicated because we have censoring. So a typical assumption is that each of the xi's are sampled from some feature distribution. This part would be the same as in classification and regression. However, the next thing that becomes different is we assume that we sample a true survival time Zi and a true censoring time Ci, and these are sampled in a way conditioned on Xi. Okay? And importantly, a key assumption is that the true survival time and the true censoring time are conditionally independent given Xi. And then if the survival time is less than the censoring time, meaning that death happens before censoring, then we set the observed yi value to be equal to the survival time, Zi, and we set the event indicator to be equal to 1. Okay? Otherwise, so censoring happens before death, then we set the observed time yi to be equal to Ci and the event indicator to be equal to 0. Okay? So this just gives you an idea of a typical theoretical setup. This is referred to as a random censoring setup. Okay? I'll say for more details on not just this, but also other basic survival analysis math concepts that I mentioned in the tutorial, they are posted in a note on the tutorial webpage. The note is titled Introduction to Survival Analysis Math. Okay? All right, so with that being said, now we'll move on to the second part of the tutorial where we're going to talk about how to actually estimate the survival function and also how to assess prediction error. Okay, so here's an example of a survival estimator. We're going to do something that looks kind of dumb, but we'll get to the more realistic setup momentarily. We'll begin by ignoring all the feature vectors. Okay? Then, of course, the survival function that we estimate is not going to be conditioned on the feature vector. So that's okay. We'll see what happens in a moment. What we can do is we can look at all the unique observed times in which there was actually a death that occurred. Okay? So I'm going to call those T1, T2, all the way up to T capital L, where L is the number of unique times of death. Then what I'm going to do is I'm going to build the following table. So I have my different times T1, T2 up to TL. And at each of these time points, I'm going to keep track of how many people died at that time point. Okay? So this will be D1, D2, D3, all the way up to DL. The other thing I am going to keep track of is the number of people that are at risk. Okay? This is the number of people that could possibly die at these different time points. And I'll call these N1, N2, N3, all the way to NL. Okay? So I'll just say this part neatly handles censoring in the following manner. So N2 is not necessarily equal to just N1 minus D1. Okay? N1 is typically going to be equal to the total number of training examples N, but some people die, but also some people can get censored. They drop out of the study. And after you subtract D1 from N1 and also subtract the people who dropped out of the study, that gives you N2. Okay, so in that sense, this table actually neatly accounts for censoring. Okay, so with that being said, now what we can do is, we have this timeline, and we're going to estimate the probability of surviving beyond time t. Again, it's not conditioned on a feature vector because we're ignoring feature vectors for now. And so initially we don't see anything from time 0 to time t1. So we'll just guess at the probability of surviving beyond these particular times. We'll just estimate it to be 1. Okay? And then the probability of dying at time t1 is, it's d1 divided by n1. And so the probability of not dying at time t1 is 1 minus d1 divided by n1. Okay? And so the probability of surviving beyond time t1 is going to be this 1 minus d1 divided by n1. And using this same logic, when we get to time t2, the probability of surviving that is going to be, it's going to be the probability of surviving from time 0 to t1, which is this first 1 minus d1 over n1 term, times the probability of surviving from t1 to t2, 1 minus d2 over n2, and so forth. In general, the equation looks like this. We're multiplying the empirical probabilities of surviving from time 0 to t1, t1 to t2, t2 to t3, and so forth, all the way until time little t that we plug in here. Okay? This thing has a name. This is the classical Kaplan-Meier estimator. I'll refer to this as estimating the marginal survival function because it doesn't depend on feature vectors. You can think of this as you have all n of your patients, you ignore their feature vectors, and then you just throw them into this Kaplan-Meier estimator and you get this estimate of the survival curve out. And there's a very, very simple way to account for feature vectors. So what we're going to do is for a test feature vector x, we're first going to find the k training feature vectors that are closest to x. Okay? So that'll give us k training patients. And if you then plug in their yi and delta I values into the Kaplan-Meier estimator, okay, so again, to be clear, we're applying the Kaplan-Meier estimator restricted to k different patients' data points. Then we're going to get an estimate of a survival curve, and this estimate does depend on this input test feature vector x, okay, because we're doing this nearest neighbor search thing here. Okay? Of course, this generalizes to weighted k nearest neighbor variance, and also there's a kernel version of this, kernel Kaplan-Meier estimator. In general, these are referred to as conditional Kaplan-Meier estimators, and these are by Bayron from back in 1981. And I'll just say that how well these k nearest neighbor and kernel conditional Kaplan-Meier estimators, how well these estimate the true survival curve S of t given x is well understood. I'll just say I have a paper from 2019 that gives finite sample error bounds, but even before I came up with this, from decades ago, people have come up with asymptotic error bands. I'll also say that these are examples of non-parametric methods, meaning that we are not assuming any sort of parametric form for the survival curves. So you might then wonder, well, what about parametric models? Before I get into the only partly parametric model that I'll talk about in this tutorial, I'll mention that there are some common variants of the survival curve that are commonly used and commonly estimated. And in a sense that will be made clear momentarily, these different transform versions are kind of equivalent, okay? So we have our survival function s of t given x. I can take the negative log of this, and this thing is referred to as the cumulative hazard function. And I'll say in a little bit why it's called that, but for now, I'll just say this is a cumulative hazard function. Then I can take the derivative with respect to time, and when I do that, I'm going to get something called the hazard function. The hazard function turns out to be equal to, in the numerator, I have this little f of t given x. This is the probability density function of the survival time being little t given the feature vector x, okay? And you can easily interpret what's happening in this right-hand side equation. It's the instantaneous rate of death at time t conditioned on surviving up to time t, okay? All for feature vector x. All right, so just to give you an example of what these different functions look like, when the blue curve here is the survival function, which again, it monotonically decreases from 1 to 0. For the blue curve, the corresponding cumulative hazard function is this dark orange curve, okay? Which is also a monotonic function, but instead of monotonically decreasing, it's monotonically increasing, okay? And then the hazard function is, well, the hazard function doesn't actually have to be a monotonic function. And as you can see here, it decreases and then it increases. So in any case, these are examples. And we just saw that the conditional Kaplan-Meier estimator can estimate the survival function. The cumulative hazard function can be estimated, for example, by random survival force. These are the random forest analog for survival analysis, okay? And back in the original random survival forest paper, they focus on estimating this cumulative hazard function. Lastly, we also have this hazard function, and this is estimated by the model that I'll spend a bit of time talking about next, which is called the Cox proportional hazards model, okay? The left two things, these are examples of non-parametric methods. Again, these do not assume a parametric form for the survival function S. In the Cox model, as we'll see shortly, it's partly parametric in a sense that I'll make clear in a moment. So before moving on, I'll just make this part clear. We can go from the survival function to the cumulative hazard function to the hazard function. We can, of course, go backwards. If I call the hazard function little h of t given x, if I call the cumulative hazard function capital H of t given x, then I can, of course, integrate with respect to time to go from the hazard function to the cumulative hazard function, okay? So now, I mean, you can see the cumulative hazard function is called the cumulative hazard function because we're summing the hazard function. We're doing this integration to go from this right thing to this middle thing, okay? And then we can negate and exponentiate to convert the cumulative hazard function to the survival function, okay? So this is the sense of why these are in some way equivalent. If we have an estimate of any of these three things, we can come up with an estimate for the other two things, okay? Possibly requiring, you know, let's say numerical integration or something like that. All right, so now I'm going to talk about the Cox proportional hazards model. And the reason why I'm going to focus on this is because it is extremely popular. This is essentially the linear regression of survival analysis, although, as you'll see, only part of it is linear. So the underlying assumption is called the proportional hazards assumption, and it basically assumes that the hazard function is of this form, okay? It decomposes in this particular way, and the parameters here are the non-negative function h sub 0. This is called the baseline hazard function, and there's also an underlying parameter vector beta, okay, which is d-dimensional, where d is also the dimensionality of the feature vectors, okay, of these x's. It's called a proportional hazards model because, as you can see from the proportional hazards assumption, the hazard function is always proportional to the baseline hazard, h sub 0, for all values of x. Okay? This is referred to as a semi-parametric model because typically no parametric form is assumed for this h sub 0. Okay? You could assume a parametric form, but it's just very common for people not to assume a parametric form for h sub 0. Okay, well, what does making this proportional hazards assumption mean in terms of the survival curves? Well, it means the following. Recall that once we specify the hazard function, we can go backwards and back out the survival function. And if you do this thing right here, you integrate and then you negate and exponentiate, then what you'll find is that the survival curves that are possible under a proportional hazards assumption must necessarily be powers of what I am going to call a baseline survival curve, capital S sub 0. Okay? So to be clear, what that means is, for example, if this blue curve is your baseline survival curve, S sub 0, then under a proportional hazards assumption, all survival curves that are allowed have to be powers of this curve. So in particular, they have to look like these dotted lines, okay? Whereas you have bigger positive values of beta transpose x, you're gonna have survival curves that are closer to the origin. Whereas if you have very, very negative values of beta transpose x, you're gonna have survival curves that are getting closer to just being all one. Okay? So here I'll just say higher beta transpose x is then going to imply, in the case where the time to event outcome is, let's say, time until death, then higher beta transpose x means that we're moving closer to the origin, and it means that we have a uniformly worse survival curve. Okay? And that also means that if we look at the mean or median survival times, it's going to be shorter. Okay, so that's what is happening here. The green curve would not be possible under a proportional hazards assumption if your baseline survival curve S sub 0 is this solid blue curve in the middle here. Okay, so basically you cannot get crisscrossing behavior under the proportional hazards assumption. And I'll just say this is a key reason for why researchers might say that the proportional hazards assumption is restrictive. And it's because, well, oftentimes in real survival analysis data, you can have, for different feature vectors, survival curves that crisscross like this green and blue curve. Okay? So in that case, the Cox model cannot actually handle this. And so you would have to turn to a different model. All right, now I'll say just a little bit about parameter estimation for the Cox model. So how this works is basically it's maximum likelihood. Okay? And it turns out that the standard way people do this will be to estimate beta without knowing h sub 0, the baseline hazard function, okay? And it amounts to minimizing a convex loss. So here, I'll just say you can use like Newton-Raphson is one of the standard ways people do it. But of course, you can also use stochastic gradient descent, okay? And of course, if you wanted to, you can add like a lasso, ridge, or elastic net regularization on beta, the regression coefficients. After you estimate beta, there's a standard procedure for estimating the baseline hazard function h sub 0. So I'll just say look on the tutorial webpage for this procedure. It's called the Breslow method. And of course, like I mentioned earlier, after we can back out a hazard function estimate, then we can back out a survival function estimate. Okay? So that's the high-level ideas for parameter estimation. The next thing I'll briefly talk about is how to interpret a Cox model after you learn the parameters. And I'll just say this is somewhat analogous to linear regression because, of course, if you ignore h sub 0 and you ignore the exponential here, the beta transpose x part is linear. And very commonly what you do is you look at the beta coefficient per feature. Okay? where higher beta coefficient for a particular feature means that that feature is associated with shorter survival time, okay? Because basically the contribution to beta transpose X is gonna make beta transpose X bigger, and again, larger positive values of beta transpose X corresponds to worse survival curves in shorter survival times, okay? So that's what I'll say about that. I'll also say that a lot of survival analysis software packages report a hazard ratio per feature, and that's just X of beta I. Here, beta I is the Cox regression coefficient for the ith feature, okay? Another thing I'll say is, just like in linear regression, if you're in a high dimensional setting, meaning that the number of training data n is similar in size to the number of features, then you can run into collinearity problems and so forth. So this is the kind of setting where you might want to use something like ridge regression or lasso or elastic net regularization, okay? So I'll say, unlike standard linear regression, of course, we're looking at a hazard function here, and I'll say that there is a standard statistical test you can use that's based on what are called Schoenfeld residuals to check this proportional hazards assumption, whether it reasonably holds or not for your data set. So that's what I'll say about interpreting a Cox model. So the next thing I'll talk about is how do we actually assess prediction error? So here the challenge is that even for our training data, we do not actually know what the ground truth S of t given x function is, or the hazard or cumulative hazard variance, okay? So what do we do? Well, the key idea is to realize that the Cox model is ranking patients, okay? What do I mean by this? Well, for our training data, the feature vectors x1 all the way to xn, the Cox model, after you learn it, basically we're ranking patients by beta transpose of xi, okay? Beta transpose of the feature vector, where higher means shorter survival time or worse outcome, okay? So basically we can use the same idea on validation or test set patients or data points, right? Validation or test set data points also have feature vectors, and we can use beta transpose of the feature vector. We can use that to rank validation or test set data points. And so in particular, a standard way that researchers use to assess prediction error is something called concordance index. And this is fundamentally a ranking-based accuracy metric, okay? And it's gonna look at the fraction of pairs of patients correctly ordered among pairs that can be ordered. I'll get to what that means in the next slide, but for now, that's what I'll leave it at. So concordance index, because it's a fraction, it's a value from 0 to 1, where higher is better, okay? And in some sense, it is like area under the curve for classification. So with that, now I'll say a little bit about what it means among pairs that can be correctly ordered. So let's go back to the example I had many slides ago for this toy data set here. So for the blue, red, and green patients, here you can see that I can actually order, for example, I can order blue and red, okay? The blue patient has a time until death that's, well, it's less than that of the red patient, okay? Similarly, I can order blue and green, okay? So even though the green patient has a censored time until death, we know that it's at least 6, which is considered better than 2 days, okay? So, however, between the red and green patients, we can't unambiguously order them, okay? Because of the censoring, because of that greater than or equal to sign. So concordance index in this example would look at the fraction of pairs correctly ordered by your prediction method. So if you're using a Cox model, it would mean for the beta vector that's learned, does it correctly rank each of these? And for example, if it ranks only one of these pairs correctly, then the concordance index would be half. Okay, if it ranks both of them correctly, the concordance index is 1. Okay? All right, so that's concordance index. I presented it for the Cox model because it's easier to explain. I will say that there is a way to extend this to non-proportional hazards models. And so as one example of this, there's the time-dependent concordance index. Okay? that works with other survival models, not just Cox. All right, now I will talk about some recent neural net advances from the machine learning community. And to begin with, I'll talk about some neural net variants of the Cox proportional hazards model. As a reminder, the loss function for the Cox model, when we're estimating the Cox regression coefficients beta without worrying about the baseline hazard function h sub 0, is given by this equation here. And fundamentally, we are learning how to rank the training feature vectors, x1 through xn, where we rank them based on the ranking score beta transpose of xi. Okay, it's basically an inner product. So this turns out to be a ranking loss. And to get a neural net variant of this is very simple. You replace the inner product beta transpose x with a neural net, phi of x, okay? And in fact, beta transpose x is a special case of a very simple neural net that consists of a single linear layer with no bias and no nonlinear activation, okay? Of course, by replacing beta transpose x with a neural net, you can use something much fancier than just a linear layer. For example, you can use like a multi-layer perceptron, or if you have like image structure in your data, you can use a convnet and so forth, okay? So the basic idea for doing this replacement of beta transpose x with a neural net, the idea is from the 90s, but there's a recent implementation that's called DeepServe that has become quite popular. And something else you can do, of course, is replace beta transpose x with a neural net phi of x and the observed time for each data point. Basically, this will give you some sort of time dependence, and as a result, this is referred to as the Cox time model. And I'll just say, for DeepServe, for Cox time, and also for the standard Cox model, for this loss function, this can be expensive to compute if the number of training data points n is very, very big. And for all three of these models that I just mentioned, you could train them in mini batches, okay, using mini batch gradient descent to avoid this n squared calculation. However, there's an additional approximation you can do, which is to replace this inner summation by randomly just choosing one of the terms in this inner summation to evaluate, okay, rather than using the entire sum. And that results in a model called Cox CC, okay? The CC stands for case control. So there you have it, a few different neural net variants of the Cox model. The next kind of model I'll talk about is something referred to as discrete-time models. And these are going to estimate a discrete survival curve or some variant of it, such as a discrete hazard function. So we've already seen an example of this back when I talked about the Kaplan-Meier estimator. And of course, it's a conditional variant that depends on the feature vector x. And basically what we get out of the conditional Kaplan-Meier estimator and also the Kaplan-Meier estimator is a discrete estimate of a survival curve. Okay, it's discrete because we're keeping track of essentially what's happening at a discrete set of time points. Okay, t1, t2 up to tl, and here also times 0. You can turn a discrete survival curve into a CDF. It turns out if you do 1 minus this function, you'll get a CDF. From a discrete CDF, you can back out a probability mass function, referred to as a survival time probability mass function. And from this, you can back out a discrete hazard function, okay, using a formula that looks like the continuous time version that I showed many slides ago. That was the instantaneous rate of death at a particular time divided by the probability of surviving beyond time t. This is the discrete analog of that continuous time case. And in this example, the discrete hazard function looks like this, okay? So by using these discrete versions, we can define a likelihood, that's in terms of the survival time PMF in a discrete survival curve. And basically you can do maximum likelihood, which of course corresponds to minimizing a negative log likelihood loss, which you can do in mini batches. So there are different ways to parameterize F and consequently S and so forth that lead to different models. Some examples of these models would be multitask logistic regression, the NNet survival model, and lastly, a deep kernel survival analysis. This last model here relates to what we already talked about previously, the conditional Kaplan-Meier estimator. I had mentioned that you can have like a weighted KNN or a kernel variant of it. A kernel variant means you can use a kernel function such as a radial basis function or a box kernel, triangle kernel, and whatnot. Deep kernel survival analysis is basically just automatically learning a kernel function to use with the conditional Kaplan-Meier estimator, all done in a neural net framework using a discrete hazard function. Okay? There is one other discrete time model that I'll mention that I think is very, very good to know, and that's called deep hit. Okay? Deep hit is now becoming very popular and it's very accurate in practice. So this models the survival time PMF a certain way. And one of the nice things about deep hit is that it can also handle a setting referred to as competing events. This is where you have actually multiple critical events of interest rather than just one. So instead of only looking at, for example, time until death, maybe you're looking at a data set where you have death as one critical event and also disease relapse. Okay, so for example, for a bunch of patients, maybe you have time until disease relapse, whereas for some other patients, they die before the disease relapses. So that's an example of what's called a competing event. Okay, so deep hit has two loss terms. The first one is like the loss that you saw in the previous slide, where I was doing that likelihood that you maximize. And of course, it's going to be based on a survival time PMF because that's what deep hit parameterizes. There's also a second loss term that basically is a ranking loss per competing event. Okay, and this ranking loss looks somewhat like the Cox loss. I'll also mention, without going into details, that there are generative models. These are basically Bayesian hierarchical models. And examples of this include deep survival analysis, deep survival machines, and neural survival supervised topic models. Okay? I'll say this last family of models in particular is nice in that it gives you interpretable models. Okay? Whereas basically these other models I've mentioned that are deep learning based, they can give you very, very accurate prediction results, but typically the models learned can be hard to interpret. Okay? Whereas neural survival supervised topic models can help you figure out how different features relate and how different topics are associated with different survival outcomes. And anyways, it can be nicely interpretable even though it might not achieve the highest accuracy. Okay? So that's all I'll say about that. So one question you might have is, how do these models actually perform in practice? And so I'll show you some experimental results on just a few of these models. I'll show you the results on some standard healthcare data sets. Okay, so here we have 4 data sets commonly used. One is on severely ill hospital patients that have a variety of diseases, whereas these data sets down here are all on breast cancer patients. For all 4 data sets, we're looking at predicting time until death. Okay, and then here you have, for example, the number of features, censoring rate, some basic statistics on the observed times. So for the support data set, the experimental results I'll show you, it's going to split the data into a random 70-30 train test split. For Metabrick, it'll be the same thing, random 70-30 train test split. For Rotterdam and the GBSG datasets, you'll notice the number of features here are the same because they're actually the same features. One thing you can do that has been done previously by other authors is to train on one of these datasets, like train on Rotterdam and test on GBSG. Okay? So in terms of the experimental results, basically what I'm about to show you is for a bunch of different survival estimators. For each of them, I'm going to do 5-fold cross-validation to tune hyperparameters. I'm going to select the best one, train on full training data set, and then evaluate the trained model on the test data. Okay? And I'll report test data time-dependent concordance indices. So here, the different columns corresponds to, well, one's for the support data set, one's the Metabrick data set, and then the last one is train on Rotterdam, test on GBSG. The different rows correspond to different survival estimators. The first 2 are classical non-deep learning based estimators, the Cox model and random survival forest. The rest of these are all deep learning based survival estimators, okay? I'm showing this just to give you a sense of the results. Deep hit oftentimes tends to work pretty well across data sets, achieving kind of among the best, if not the best, prediction accuracy. At least for these data sets, none of the methods achieve a concordance index close to 1. And I'll just say it's unclear how much better we can do. It could just be for these prediction tasks, they're fairly hard given the features that are present and possibly also given the data set sizes. And something that I'll say again momentarily is that the prediction accuracy for deep learning methods, they can be better than classical methods, but it could be, not by too much, okay? In terms of the raw absolute differences, okay? So anyways, this hopefully gives you a sense of the prediction accuracy of some deep learning based methods versus classical baselines. Now I'll move on to open challenges, and the first thing I want to get at, this is related to the experimental results that you just saw. Basically, oftentimes the performance gain from using deep learning or neural net based approaches could be something like 0.02 or 0.03 in concordance index. It's unclear whether this is like a large enough gain for those particular applications of predicting time until death. One of the issues is that many of the standard survival analysis data sets that are available aren't that big, okay? In terms of, well, the number of data points might be in the thousands. Sometimes if you're lucky, they're in like the tens of thousands or so. The features tend to be like in the tens. Sometimes you might get lucky and be in the hundreds. But really, right now, in terms of survival analysis data sets, the numbers aren't that large. And one of the open challenges, I think, is for the communities that are interested in predicting time to event outcomes to come up with much larger benchmark data sets. I will mention there is one fairly large public benchmark data set I'm aware of. This is data from the music streaming service KKBox. And we're looking at predicting time until users unsubscribe from the streaming service. So this data set has close to 3 million data points and some tens of features. And deep kernel survival analysis can achieve a state-of-the-art concordance index of about 0.89. And classical non-neural net baseline XGBoost can get a concordance index of about 0.87. Okay, so I mean, this goes back to what I was saying earlier. Right now, the boost you see from using a neural net approach might only be like 0.02 or so. And it's not totally clear whether that's a practically meaningful enough difference to justify using deep learning methods, especially if they can be harder to interpret. Okay, at least for this KKBox data set with concordance indices that are fairly high compared to the healthcare examples I showed you, it could be this data set is relatively easy to predict compared to predicting time until death. Okay, but in any case, that's an illustrative example. Getting back to something I talked about before, a lot of work on the machine learning side has been focused on prediction accuracy and not so much on interpretability. Okay, so if you do want an interpretable model, the standard approach is basically to use Cox model, maybe with, let's say, lasso or elastic net regularization. I guess here I'll mention there are other parametric models that people might use as well, such as like accelerated failure time, log normal, log logistic, and so forth models that can also be fairly straightforward to interpret, that you can also add, lasso or elastic net regularization. Deep learning approaches, they can give you higher accuracy than these Cox or these other parametric models, but it's unclear if the performance gain, the accuracy improvement is large enough to justify the loss in interpretability. Okay, so of course it depends on whatever application domain you're working in. It depends on a domain expert to provide input on what parts of the model should be interpretable versus what parts of the model we don't really care about interpretability, and can then use whatever black box models that we want to use to estimate those aspects. Okay, this I guess is like how the Cox model is semi-parametric. Some part of it that's parametric is the part we care more about in terms of interpretability. The baseline hazard function is often just something we care less about, so we don't specify a parametric form for it. Okay, Of course, it would be nice to have methods that achieve both state-of-the-art prediction accuracy and that are easily interpretable. I think this is an interesting open problem. And I'll mention that there has been a lot of work recently in machine learning on explaining black box models. A lot of these ideas, such as SHAP and so forth, could be imported and tailored for survival analysis, but they come with the same pros and cons as they do when analyzing black box models. And some researchers would argue that you should just use an interpretable model to begin with rather than learning an uninterpretable black box that you, after learning the model, you use one of these model interpretation methods to attempt to interpret the black box model. Okay, so something I'll mention that I think is interesting for the community to think about more is survival time error bars. Okay, so it turns out that it's now possible to construct survival time error bars that actually are statistically valid. Okay, and an example of this would be something like, oh, we predict, let's say Alice, to have with probability 90% survival time 30 plus or minus 20 years. Okay, so here this 90% is referred to as a coverage level, and this plus or minus 20, this is like an interval width. Here the width is 40 years. Okay, basically these are like confidence intervals. Well, confidence intervals are for the model parameters, whereas here we're looking at prediction intervals. Okay, so basically what you can do is you can plot prediction interval width as a function of coverage level. Okay, you can compute this for any survival estimator you want, and this is an interesting way to look at, depending on what interval width you want or what coverage level you want, you can see what kind of model achieves, the lowest interval width. For example, let's say you're like, oh, I want a coverage level of 70% and I want the lowest interval width possible. What achieves that? In this example, it'll turn out to be a deep hit. Okay, whereas if you want a high coverage level and as low of an interval width as possible, it'll be a Cox model. Okay, so I'll just say here there's a trade-off that's similar to confidence intervals. As you might know, if you have like a 90% confidence interval versus a 95% confidence interval, as you make the coverage level larger, your interval widths become wider, which means that the interval you have is not as useful when it's wider. So there's a trade-off between interval width and coverage level. A plot like this can help you decide on what model to use. Okay? All right, cool. So that's what I'll say about this. And this kind of idea is not yet all that popular, but I think it is a valuable way to view a bunch of these prediction problems in survival analysis. So some other things I'll talk about is that there are some other problem setups that we didn't talk about. So we specifically focus on talking about right censoring. This is when you have that greater than or equal to sign, so a lower bound on survival time. But it's also possible to have left censoring, where you have an upper bound on a time. So this could be like time when a child learns a task. You finally observe, oh, this child can do something. Basically, they learned it before you know for sure they learned it. The exact time when they learned the task can be censored. So I'll just say it's possible to modify right censoring methods to work with left censoring. Also commonly, you might have something called interval censoring. Okay, this is where you know that the critical event happened within an interval, but you don't know exactly when in that interval. Okay, so for example, a patient gets a negative COVID test and then gets a positive COVID test, then you can say, well, time until getting COVID is it's within an interval. Okay, but we don't know the exact time. So yeah, I'll just say there are some methods for dealing with this. Some other things that I didn't really talk about is that feature vectors can have missing values. And so there is an issue of how do you deal with imputation. I guess much earlier I had an example where I just filled in all the missing values with 0. That might not be what you want to do in a lot of practical scenarios. Something else is oftentimes you might be doing a time to event prediction task where time dynamics matter. Okay? Maybe you have feature vectors that are actually sampled over time, and maybe they're irregularly sampled over time, and you want to, at different time points, predict time until a critical event happens. Okay? So I'll just say there are a bunch of researchers now that are working on these kinds of methods The theory here is less well understood, and as you can imagine, it's much more complicated. That's all I will say about other problem setups. Now I will give a very inexhaustive list of software packages available, starting with some packages in Python. Here we, for example, have Lifelines, which implements a bunch of classical models, including a few that we talked about, such as the Kaplan-Meier Estimator, the standard Cox model, and also regularized variants of the standard Cox model. There's separately a fairly robust implementation of regularized Cox models that's referred to as GLMNet Python. This is the official port of a very popular package in R called GLMNet that includes regularized Cox variants. Okay. Next up, we have PyCox, which provides a unified framework, including PyTorch implementations for a whole bunch of different neural net-based survival estimators. Okay, this is very nice because it's a unified interface for a bunch of these models and also a bunch of different data sets. In fact, the experimental results I showed you earlier were implemented largely in PyCox. Next up, we have PySurvival. This includes a reference multitask logistic regression implementation by the original author, as well as Python implementations of random survival forests, which I mentioned, okay, as well as some other classical models. I'll mention that some of the neural net-based methods, such as DeepSurv, DeepHit, and NNet survival, also have reference implementations by the original authors. Okay, moving on to some R software packages. For the most part, the R software packages are for classical models rather than neural net-based models. Okay, so you have your usual implementations for Kaplan-Meier and standard Cox models. As I mentioned in the previous slide, there's something called GLMNet that includes very robust implementations of regularized Cox models. There's also something cool called HD-nom. This is for making nomograms. This is a simple visualization you can create to help readers interpret Cox models, the beta coefficients. There's the reference random survival forest implementation by the original author. And these last two packages I mentioned here, these are for competing risks, which I didn't really talk about. These are using classical models rather than DeepHit. Okay, and that's it. I'll just end the tutorial with this link to the tutorial webpage. Again, all the material that I presented is available for download here, along with kind of additional information that I didn't talk about. So yeah, thanks for tuning in to my tutorial.